Okay, audio check. 1, 2, 3. Sounds okay to me. We can get started. Ladies and gentlemen, welcome to the Discourager of Hesitancy. We are building a game with no game engine. This week has been full of interruptions and short streams, so we are spending more time on an experiment than we normally would. The thing we're pondering is music in our game, and we could do pre-recorded music, which would explode the size of my executable, but would be easy, right? Then it's just a matter of maintaining a playlist and not actually that exciting in terms of coding difficulty. Or, and we can, we're sort of exploring this idea, we could instead use tonal generation, waveforms like sine wave, sawtooth, triangle wave, to generate our own music, which would be much more compact and space efficient, but needs more work up front. So we're using our short interrupted streaming days to explore the idea and see if we can make something that sounds okay. If it works out, we may do that. But it's hard to know, which is where we're at in the experimental phase. All right. Last time, we were slowly expanding our list of opcodes. What we're doing is building up some very basic primitives for what a song would have to do, which you can kind of see here. We've got our tonal frequencies defined, and then we write instructions to play a note. So if we want to play a note for some amount of time, it means that we put into our instruction buffer the play operational code and then tell it which tone by index. And then we can have to wait for some amount of time before releasing the note, right? And when we have these very simple, basic, primitive instructions wrapped up in some abstraction, well, we end up with something like this, where we set the volume, we can play a sound for 3/8 of a beat, and then wait for an eighth of a beat, and then increase the volume and do it again, right? So we slowly get louder and louder, and then after we go up the 5-note scale for C major, we can change our beats per minute and change to a triangle waveform, so it'll sound different, and then wind our way back down that scale. And that's where we're at right now, which might sound something like this. And that's it. That's where we're at. So we need to make it better, because right now that's not powerful enough to make good sounding music. Which brings us to our list today. We're debating a couple of different options. So it'd be nice to be able to transpose our music up or down. So let's see here. I guess here's the deal. A song starts with initial conditions, like 60 beats per minute, right? And in the song, we can change that tempo. So we have initial conditions, and then we have running conditions. And so we have absolute adjustments and relative adjustments, which is what we were looking at here. We were looking at adding, so we have this ability, we can set the volume and we can set the beats per minute. But we can also adjust the volume by an amount and the beats per minute by an amount. Those are a couple of things we might want to do. We haven't added those operational codes yet, but we can. Set tone offset. Maybe something like that. And we can adjust the tone offset. So setting the tone offset is literally just the number of half steps up or down. I think that's the plan. Volume adjustment. Let's just get tone offset done here. So this is our BPM, our tone, and then unit 8T m_, tone offset. Tone offset is going to be 0. Now, whenever we play a tone plus m_, tone offset, and you shouldn't hear a difference. The way we're doing things now. Set volume, set waveforms, set BPM. This part I need to read out a signed integer. I guess we can do it like that. That's reasonably descriptive. We scan that value. That can be plus or minus, in theory. Then we want an option to debug things. Set one offset. I don't want to rename everything. So let's rename it. Let's see here. To arg uint 8. This is the most popular one by far. Then we have float. Okay. All we have to do is m underscore tone offset equals arg int 8 and break. So where we build up our test song, we can totally shift this up or down, right? So let's wait for half a beat. We're going to run back up. Then we'll run back down. Oh, we should. We'll go back to sine wave. We'll go back to triangle. And we don't need to play with the volume anymore. We've already listened to lots of volume changes per note. Hey, Javette, good afternoon. How are you doing? In fact, I think what we're going to do is double our gain and our losses, so it sounds a little bit more. Our contrast 0, 5. Go back to the sine wave. We're going to set a normal 0.1 volume. We'll play our way up and down. We'll still keep the fast tempo. And now what we want to play with is transpose. Oops. Set tone offset. Okay. So what we want to do is transpose 1 and -1. So we'll go up a whole step, so 2 half steps, and it'll come down 2 half steps. Then we'll make the relative adjustments of an option. Or maybe we don't. Interesting. Set tone offset -2. Maybe we should have slowed our tempo down so I could hear better what's going on. Let's slow it back down. Easy change. 60. You good? Thanks. Sitting here in my new office. Just got your monitor up and running. Good. Having the right number of monitors is key. So you're liking home life, huh? Instead of apartment life. Good. You got a pet yet? A goldfish or something? Okay, that doesn't quite sound right to me. Okay, so we're going to half beat. Then we play, wait, play, wait, play, wait, play, wait. 1, 2. Oh, where's the C? 4. Okay, so that would be that thing. So down to C, C, D, E, F, G, and then G, F, E, D, C. Play, wait, play, wait. And then C. Yes, house life is much better than apartment life. No, no goldfish yet. All right. I don't really go in for goldfish, but some of those like beta fish, the Japanese fighting fish, those are pretty cool. Or like get a 50-gallon saltwater tank. Set the waveform. Play. That play doesn't have a weight. Release. Play, wait, release. What is happening here? G4, F4, E4, C, D, E, F, G, G, F, E, D, C. where we call play. We should do that. Is there a halt somewhere where it shouldn't be? Oh. We should put a halt in, so at least we know where to halt. So let's explain what's going on here. Permission denied, I agree. Yeah, a really big aquarium, one with all the cool colored fish that are brightly colored, and snails and lampreys and all that stuff. So we say go down 2 half steps, triangle wave, play 53, then 51, wait 0 beats, and then halt. Okay, here's a thought. We need to do a full clean and debug. I don't know, I'm not really much of a pet person. The whole dogs and cats thing doesn't work for me. I figure fish. Fish is about as close as I'll ever come to owning real pets. Every time I'm around dogs or cats, my allergies just get murdered. Ever since I was a little kid. Anything with fur, pretty much no good. But I've never had an allergic reaction to a tank of fish. When I was in high school, we had a science teacher who had a big old 50-gallon tank full of goldfish, like 20, 30 of them. And then he had this little, like 2-gallon tank off to the side with a piranha in it. And once or twice a day, we had to feed the piranha. That was pretty cool. I love my dogs, but I hate them too. Yeah, well, I think it would be different. Like if you're out in the country, you can kind of let them run wild a little bit. Like dogs need so much room and energy to spend. They should be like they love running around and playing. But you get them inside of a city, and all they got is this little tiny yard. They just have too much energy, I think. Koi fish are cool to own. Okay. Nice, nice. Well, koi will grow as big as their container, right? They'll get huge if you have a big enough container. My dogs will never come back if I let them run around. Yeah, you kind of have to have the right setup and the right amount of training before you let them run wild. Okay, that's good. I was worried there. I think it was just memory alignment issues during recompile. So good to go. Okay, so Where was I? Song.h. One could argue that we've got these three done. I'm going to hold off on these three opcodes here. I don't care. If we want to do variable rate adjustments or variable adjustments, I'll add it later. I think that's the right answer. Let's not get bogged down. We're just experimenting still. One sine int 8-bit. Yeah, let's not get bogged down in. We're just prototyping a Turing machine. What exactly are you setting up? The ability to load songs like MIDI? I'm skipping MIDI. We're doing it ourselves. Homegrown. We're just playing with the idea. It'll be, well, I don't know. I don't know enough about the MIDI spec to say how much will be like it or not. I like discovering things without polluting my mind with what's already been done too much. This is all prototyping. We're not going to waste too much time on it. Oh no, we're going to add layers of abstraction, so it'll get better. Like if you look at what we have to do to play a note, we say, anyway, we're building up basic building blocks. So I would say transpose is fine. Beats per minute are done. Oh, oops. Let's move all our tasks over. We got transpose and speed offset. Relative adjustments to BPM to tone offset and to volume. We don't care about this right now. Okay, so now we want to add a new layer of abstraction. Okay, so what we have right now is we say at instruction 264 byte, at the 264th byte, the opcode 2 is to play the tone at index 50. And so that's going to do is going to start it and hit play. Then it'll wait and then release that note. That's not really how we want to do it. What we want to do is tell a note, you play for this long. And we have a couple of options for that. The sound itself, I can set a duration. And I think we'll use it. Then we don't have to manage on and off of a note. Let's see here. SMW Central has songs in SPC format, native format for playing back. Yeah, but it's all in split tones like you're doing. Yeah. I mean, the cheap, easy answer is probably to go to pixabay.com or something like it. I'll just paste the link there and just look at the free songs and just pick a bunch and just put them in a playlist in our embedded in our executable and make a playlist. That's the easy answer, but I knew I would have a lot of interrupted streams and short streams this week, so we're playing prototyping. We have a lot of things we can play with and try this week, but next week I'll have to make a decision what I'm doing about my songs. Okay, so part one, each sound will have a duration when we play it. I think that's the right way to go. So let's say what we got. We can change the BPM in mid-song with an instruction. And also define a tone offset to transpose with an instruction. Tone offset and BPM adjustments. I can set the BPM, but I'm not calculating an offset from a baseline. So there's no way to say for me to say speed up 10 beats per minute. Oh, and then go back to 0, which I kind of like. I made my music for my game with AI. Nice. AI EDO. I just need to find an easy way to dump it into a module or the exe without loading it bad. Yep, audio gets big. It's a huge file. Compressing it can only get me so far. Make it mono channel. That'll cut it in half. And then I don't know if you're exporting it as like floating point samples or 16-bit PCM, but if it's MULA encoded mono channel, like that's 1 byte per sample. You can also downsample it to a lower frequency. Depending on the quality of the audio, you might be able to get away with that without distorting your sound too much. So let's see here. Let's see. I'll look up some links here real quick. MULA encoding. This is something we're going to do later on this stream, but something like this to encode your audio. Mono channel, which you can do MULA encoding and mono channel changes with Audacity. Just open up your audio and you can export it like that. Yeah, then it's just 1 byte per sample. I don't know, a few different options. Then you run your compression algorithm over that. I actually want BPM differently. Let's go play with that real quick. Do we? Let's do this with BPM, 60 over BPM. And now we want a BPM offset. And whenever we want to know seconds per beat, which shows up in only 1 calculation right now. Hey, there's a lot of techniques to use. I just need to execute something and see how it goes. Yep, you can't know until you measure it. JTL, how are you doing? Howdy, howdy. Seconds per beat. I'm going to separate this out as a function, even though I don't need it right now. I know I'm going to need it shortly. So, seconds per beat right after stop waiting, which is going to go away shortly here. BPM plus m_score BPM offset, all under 60. I think we're going to use this in a couple of different ways later. And now when we say set BPM, it'll instead be offset. We want to adjust the volume the same way. Doing good today. Donut countdown is 0. Yes, my kids are in the kitchen right now making donuts. I hope they bring me one when it's fresh. It's going to take a while to rise, though. That yeast dough takes a while in the cooler weather to rise. So I'm not going to have anything in the near future, but I know it's coming, so life is good. Very good. Okay. All right, so here's the other question. Set volume. Do I want to do that? Have a baseline volume and then adjust relative to that within the song instead of setting absolute volumes? I think I kind of do. We can have an offset or a factor. So we can like double or halve our volume, or we could just say add 0.1 or subtract 0.1 to the volume. Not sure. Not sure I want to play that. So many options. Like, this is part of the fun of building something like this, is you're kind of discovering what the primitive operations are that you need to get the effects you want. So I can set the volume to 0.5 or to 0.2 or whatever. I would say the baseline of the song is set at volume 7, 0.7. Then we adjust up and down relative to that. Is that a better interface or not? Volume should probably be a float. Right, so we have our baseline beats per minute. We have our tone offset of beats per minute offset. int 8 volume offset I think this will be better. M_floor volume offset equals 0 volume. We should just start at something normal, I guess. Volume plus the offset. These are both floats, volume and volume offset, yep. Then my BPM is this. These are like the effective BPM and effective volume, which you can even call it that. That way it's clear that it's not like something a user would use. Okay, so again, I'm just trying to discover what the right underlying primitives are. Set volume offset. This probably needs to be a float. We can force it to float just in case somebody does something silly. Set volume offset. Weight is a float, right? Okay, I think the types of things are generally okay. Let's see here. Where's BPM? set BPM offset. Right 1 byte. Then we need to rename it. All right. So we're not using that. We're not using that. Instead, we use write uint 8. Write int 8. Something irritating my eye. What's going on here? Right float. Those are the only things I'm really using right now. You can always revisit these if you feel like it. Uint 8. And right float. Okay. Okay, let's rename this to right uint 8. Yes, 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 yes. Ooh, that's not. This one is right float. Yes, no, that's an int. Yes, yes, yes. Yes. Nope. I think that means all that's left is right int 8. Which now we need an awful lot less casting, I think. They should auto cast a lot better. Oh, my eye. Okay, irritated. Okay, so now when we set volume, what we really want three, one, oh, 0.0103, 03, 01, 1, minus 0.03, minus 0.05. Then we just set our volume offset to 0. The rest is fine. Now BPM is also relative. So BPM plus 60. And then BPM offset back to 0. I think this is a better setup for what we want to do in the future. It's more consistent. in our implementation and interface to the developer. Okay, now when we say play, oops, here, we do that, we set our tone, sound.set volume to our effective volume. Then we play. Easy. Okay. Then volume, tone, BPM. Our volume offset now, though, is a float. BPM offset is that. Tone offset. All right. Let's see how many things I broke in one shot here. Well, oh, well, set BPM offset. Get that. Hey, we actually didn't break that much. Good. The tones themselves still sound like garbage, but that is further down on our journal list. BPM, volume, and tone are now treated as song has a base value and instructions are to modify a running offset. Okay, I think that's more consistent. Git status, git add, commit, transpose, BPM shifts are working. Okay. we can play out C major scale. I don't want to count it yet, though, until we've redone this part. So, like we already discussed in our song, I want this note to have a sound. A note has a timer, but I don't think I need this timer, actually. This note will get other things. I'm just thinking while I line things here. So let me say play a note. A tone and a duration. And I don't need a release anymore. Tone and duration, which changes what play means, and we don't need release. So we can get rid of release. 1 byte song tone index, and then a float duration. And it's no longer dt, it's fractions of beats. Numbers of beats. Okay, so nothing should change there. Oh, that's not true. We've got 3/8 and then wait for a half beat. I think. We'll take a look at why here in a second. In which case, let's just do this in a whole beat. Whole beat. Okay. So that's the writing part here. Play. We are scanning that, and we shall scan our float. Set tone, set volume, set duration of arg float times time underscore seconds per beat. Module 0.3 float which is hard float time beats. And now we don't have to release the note. And in fact, release goes away. And wait, maybe it's more of an advance than a wait. Let's see how badly we broke it. Oof. We don't need that. We don't need stop waiting anymore, that's right. Means we don't need the... Oh, we need our own egg timer. We do need this waiting. But we need our own egg timer. Not the one in the note. Okay, come on. Now we set this up here. X, U. Okay. That's it. Basically, our main song timer. So this tells us we've done all the instructions at the current place, wait for some amount of time before finding the next instruction. This is what this is for. And now, when we say wait, in the wait is waiting, arg float, M timer, M timer. There we go. Now the timer's been pulled out of the sound. Gonna put this back in. You know what? Everywhere I see this, I just need to replace it with that. And there's one that snuck past us. All right. One extra deleted character. Well, installing the toolchain for Clang and MSys. We'll see how things go. Yeah, I think Clang is objectively probably a better compiler than GCC. I should make the switch one of these days, but I'm not there yet. Okay, close. Not quite what I want yet, but I think it only has to do with these long waits at the end. So let's go for modifying our song here. Play this for a whole note, then wait for a whole note, and then so instead of a whole, well, we're going to come in here with 7/8. We're gonna make sure that this ends before the next thing happens. All right, we're getting there. Yeah, I submitted my request to get access to the Jai closed beta. I hear it can take a couple of months before you get a response on that, so. Yeah. Okay, sounds good. So that is part 1 of the next stage, which I guess wasn't clearly aligned here. Play note duration should be tracked by the note itself and not timer duration. No longer needed to, let's see here. No more note release. Note tracks its own duration. Wait is only used to delay until the next event, processing event. And song has its own timer. Okay. Play note rest in fractions of a beat. So that's all done. And we are definitely playing a C major scale. Ode to Troy. Did I write piece somewhere? Okay. Yeah, there's so many things we could do with this. So fun. Okay, Ode to Troy. Part of me. Well, okay, so here's one thing we want to do. We have all these halt, wave, wait, volume, all these functions. I want to break those out into something more. Like a function, or is this okay? It's okay for now, I guess. Okay. Well, no, I don't want to get into that part. Ooh, let's see. Let's make a shortcut here because there's an idea I want to pursue here. Play advance tone and beats. And you'll see why in a minute when we get here. I bet we want to play and then wait. Play the tone, but we're going to do a little bit of beats. Minus 0.0625. We're going to wait 0.0625. Instead of this, play and advance half note. Half, half, half. C, D, E, F, G. Full beat. I want this bit of abstraction here as well. Just make sure it runs. Nope. The volume plane advance. I want to advance after the half note, but the note doesn't hold over that full duration. Oh. I know what I did. Not too bright. There we go. Easy fix. Okay. Alright, so let's add that little abstraction everywhere since it's working. I much prefer that for now. Okay. Search for play. Oops. And advance. Okay. There we go. Okay. Now, Ode to Joy might not be too bad. Ode to Joy notes. Somebody's got to have a. Nobody? Well, we could guess. I mean, we're not in any hurry, right? This is all prototyping stuff. Let's see. Major scales. You know what? Let's make this a. Ooh. Yeah, whatever. Ode to Joy. Oops. Let's do it with the triangle wave. We don't need to wait when we start. The volume can be default, everything else the same. Dun, 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 dun. So, oops, whoa, okay. Play in advance. Tone of, I guess C4. No, C, E, E4. Dun, 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 dun. We'll take the whole beat. E4. Dun, dun. F4. Dun, 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 dun. G4. Dun, 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 dun. So this is D4. Dun, 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 dun. So this is a quarter or a half of a beat. So dun 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 dun. Oop. Dun 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 dun. So like 3/4 of a beat. Dun dun. Maybe 1/4 of a beat. Let's just see what happens. 1/4. All right, fine. We'll be more consistent. All right. I feel like that is extremely slow. We're just gonna. We're just gonna add 60 BPM. We're gonna double it. I may have been thinking of like a 4/4 time, and so I'm giving quarter notes. Yeah, so blah blah blah. We'll think about it. Okay. Not 3/4, but rather like 1.5, and then 2/4. So whole note plus a half note. Hey, we can do this. 1/2. This is actually shockingly close for a first try. I don't know why I put 3/4 in. I knew it was longer than a whole note, or whole, not a whole note. I need to either decide whether that's a whole note or a whole beat. We'll ponder the mysteries some other time. Like how close do I want to be tied to actual musical notation versus my own internal mental mathematical model. We can actually hold that last note a lot longer. Let's see here. So 3, 4. This is a 4/4 count. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2. Let me just go with the hold here. I have it 3/4. You can see how from very, very primitive operations, we can pretty quickly arrive at abstractions that let us put one line of code per note. That sounds pretty good to me. Not bad, not bad. Then, for the interested party, we probably have a rest for maybe a whole beat, whole note. I don't know. And again, right now, not clear. Doesn't matter too much just yet. I think I have been treating quarter notes. So maybe I just change whole to 1/4. Are these beats or quarter notes? Because right now, 60 BPM. See, this sounds like 60 BPM when we play it this way. So I wonder if I have a multiplication somewhere that's wrong. Anyway. Dun 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 dun. Dun 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 dun. Dun 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 dun. Then we go to D4 earlier. D4 done. This is the whole plus 3/4. Dun dun dun. So it'll be C4 here. That's basically the only difference in the second phrase of the song. C4, C4. That should be the first couple of bars. That should be enough to prove that we can do things useful in terms of laying out music. Oh, we are so good. Look how good we are. Okay. Playing chords is next. So added a quick test for of a couple of phrases worth of ode to joy. Basic ode to joy. First two phrases are in for testing. Actually, it doesn't sound that bad. So playing chords is a big deal. We will like that one. And I think this one, making the tones sound better, is going to be a key. So time for a quick restroom break. Then we'll work on chording. All right, be back in a minute. Okay. All right. So we can play a little bit of Ode to Joy, but that's not nearly good enough. We need a pool of notes. And when we say play a note, it should ask the pool of notes who's not busy, cue it up, and then after it's played, it's returned back to the pool as idle. So this is very similar to our scheduler, but on a per song basis. Maintains its own duration and availability. So one thing that each song now, each note needs is we need a status. Do we make note status idle waiting running note dot sound dot status equals song note status idle. Later on, we can actually break this out into a whole separate class if we want to, make it all fancy schmancy. Notes, or note pool, int underscore note count, static const expression, if I could type, note count equals 12 notes. It kind of doesn't matter. Hello? ManCow90. Nice username. Welcome. Thanks for the follow. Thanks for watching. Always happy to have a new person in the group. Let me know if you want any like project breakdown or if you have any questions about anything. Usually I just code stream of consciousness out loud until somebody asks a question. Then we stop and talk about it. Right now we are in the polishing phase of the game where everything is functional and working, but we're trying to decide how we want to run our songs, our background music. And because of the nature of my week, I decided to take this week to like prototype a waveform generator and build on top of it to build a well, we've got the waveform generator, but build on top of it to make songs. So we just got through the first couple of measures of Ode to Joy with a triangle wave, and we're just slowly making things better. If we make it sound good enough, we may go this route. We may go snag some free music off the inner Googles, and just crank that in. That's not hard. It's a lot less work actually. Or maybe I'll have my sister compose something for me because she is very musical, very musically talented, very musically skilled. I just kind of fumble about, so we'll see how that goes. But yeah, thanks for the follow. I do have a Discord if you want notifications when I go online. There is not much traffic, not much spam in there, just the announcements. But yeah, feel free to drop in if you have any questions. You can ask them in there too. So what we're doing is kind of building a musical Turing machine, right? So it ends the song, waits for some amount of time for the next instruction, play a note, given a tone and a duration, set the waveform for the note, set the volume. That is no longer correct. That is a float. Sorry, I'm doing my, I realized my notes to myself are no good. But we're just prototyping. Like, we could make things a lot fancier, a lot better, more, more stable. We just aren't. We won't spend the time on it unless we decide it's worth pursuing. Okay. So in song, one of the things we want to do is get a note from the pool of notes. Notes at that index dot status is equal to idle. Then we are done. Result equals standing notes at that index. Return the result. While we're just in development, assert result not equal to null. Good enough. Right? So now when we say play, we can instead get a note. Star note equals no pointer. Note equals get note. Oh, interesting. Set waveform. Okay, well that has to change. Where else do we have m underscore note dot? Set waveform and set them all to idle. So they are ready to go. Stop all the notes just in case they're playing. Then we set all the notes status. Equal to idle. So every note is available. We do our timer thing. This is important. While we're running our update, we have to clear out any completed ones. So if underscore notes at index status is equal to running and if the note is not playing, we set it back to idle. Like once the sound is done, it becomes idle and available to reuse. That also means in here when we say play, we get that thing. We set it to waiting so it doesn't get picked up before it can start. Why is that what we called it? Waiting or something? Yeah. And then as soon as that sound starts playing, where's play? Play. Song note status playing running. Call it playing. So in the future, if we multi-thread things, if we get the note, it's already set to not be got by some other item somewhere. Status playing goes until the sound itself is done. None of that should be too crazy. And nothing we do should not change the running of our current song at all in terms of sound. In fact, one could argue getting note, this will always be 0 because of the way that our current song is written. Note pool. Okay. Oh, that's not right. Anyways, doesn't matter. Let's see. Okay, okay. Okay, let's see here. Okay. Okay, that should be that piece of refactor. With this, like I said, everything should come out note 0. In the printout. We aren't going to be able to see that very well, so let's go to Let's not debug this song. I'll output all of the opcodes and arguments as we go. We don't really need that right now. Make it easier to spot the indices we're interested in. So this will make it so we can have a chord where we can say play note, play note, play note, advance. Play note, play note, play note, advance. And it'll grab whatever notes are available, cue them up, and send them off. So this will notice do things like where you're sustaining the melody note, for, quarter for a quarter note for one beat, and then you want like the alto line to come down 2/8 notes. We can start them both, advance an eighth note, start the next one, then advance as far as we want. I think that weight should be called advance. So that's the idea. That's why we're having a note pool. This should not make any difference, but we should see that the note being selected is the 0th one over and over again. Okay. The instructions being printed out for one. I'm not even sure that's that useful anyways. Oh. And then break. Okay. Here we go. Something like a little ode to joy. Yeah, getting note 0 over and over again. Okay. I want to just try one note just to see how it works. C4. We'll go with the double beat. This will take up both of these lines. Doesn't change much. That should be enough to let us know if we can play those two notes at once. Okay, so here's the thing. We can go volume minus 0.05, so it's a little quieter. Everything is generally triangle wave, right? Didn't we? Sine wave. This is the whole interface is going to change over time. It'll be fine. So we're going to make it quieter. We're going to play a different instrument. We're going to play it for twice as long. After which we return to form. So this will be volume back to 0 and back to triangle. This is where the idea of tracks comes in, but that's okay. So we can play chords technically, even if right now it is verbose to do this. It does work. One, two, three. We make this an E3. So basically, this is a chord. This would be a chord. We're going to go with E4. Just to see how it sounds. So here you can see where it started playing that chord. It needed those other notes. But we can indeed play chords, even if it is verbose. Oh, not bad. Now, it's not pretty. And maybe now is the time. Well, we can. Here's the C4 again, where we will play. Oh, here, what are we doing? We're playing E, we're playing C, we're playing F, G, we're playing E. So we're down a third from C. Would be B, A4. At the same time that's happening, then we go up to E, which would be C, and then the D. Yeah, basically E plays C, G plays E. C plays A. Where's my A? It is. We'll play another round of A here. Ode to Joy with chords, although bad chords. And here we go. So A4 should be A3. That's what I learned. A4, 3, A4, A3, A3. And then somewhere up here, like this one doesn't really fit here. When we go to the pair of G notes, I don't think that E4 sounds good there. Anyway, let's just see how that sounds. Yeah, so I'm no great musician. That doesn't sound great, but we can do chords, we can play things. I think it sounds like to me, when we have this pair, it would sound better if we did this. Basically a delayed drop into the pair. To see what that much sounds like. Okay, well, Ode to Joy with some basic chords is in and working. The interface to create those chords isn't beautiful, but the pooling of the notes is working. Note pool is in song and working. Chords can be played. even if right now the coding is a bit clunky. Like that code interface isn't great, but everything we need is there. Git, commit, and this is a prototype, so it's fine. Chord, let's see here. Note pool is in, and chords can technically be played. That is not nearly as hard as I thought it would be, which is good. Now, make the tones sound better. I don't know what this means yet. As a volume. So right now our song has only one track. It'd be cool if we could have two tracks of instrument. I don't know that I want different tracks to have different BPM. Maybe that still stays in the song. The transpose tone offset probably doesn't need to be. Ooh. Is there also a shared mem space? Enabled flag, volume, instrument instructions. And memory. Question, is there also a shared mem space? Okay. Make the tones sound better. So what I'm gonna do to start with, just so we can hear better, I'm gonna take out the chord pieces. That's why I broke them out like this. I can easily find and comment these out. And you'll hear a lot of clipping at the ends of these things, and I'll explain why in a minute. And the tones just don't sound good because they're so mechanical. You can hear a little click at the end of each of those, not each of the notes, but often. Okay. What's happening there is we have a plot. And on this plot is a sine wave. And do I think I could reasonably draw a sine wave? Probably not. It would be better. Hmm. Maybe it looks something like that. Then it also curves down below, underneath like that, right? And we'll just invert this wave. Then we need to add an offset, which is how far? Right about there. There, something kind of sine wave like, right? Now, if when we say stop, when we've run out of samples, if the sine wave is near 0, it won't sound like it's clipping. But if we stop right when the sine wave is near a peak or a valley, it doesn't matter. Then you will hear that clip because your audio hardware has a high voltage, or a voltage relative to 0, and then it has to return to 0 in your speaker. So it's going to snap that voltage in the magnetic coil to 0, and that's going to be that pop. So some notes you won't hear the pop, other notes you will. Right? So that's one issue. So let's do that. Let's see here. Sine wave audio pop. 2, it sounds mechanical because it's generated. Mechanical sounding. Add warmth. Well, let's see here. Hard in. So as soon as we say go, this volume is full volume, right? If you look at an actual sound wave, let's actually bring up a sound in Audacity. Let me see if I can find a reasonable one to play with. For us to look at, like more like a ding or something. So let me dig up a sound file real quick. And we can look visually at it. Sounds. Wait, what am I doing? I know how to find one quickly. More quicklier. Not that one. This one. Okay, I need a single tone, maybe musical. Something like piano. Or nope, I don't want that one. Let's look at a marimba note. All right, let me find that file in the thing then. Resources, sound. So music, marimba note. Yeah, that's probably, or xylophone. We can look at both. Music, LMNOP, marimba note. LMN note. Here we are. Open with. Oh, wow. Okay. Open Audacity first. Okay, now I can share this. Where's my thing? There it is. Okay, Audacity. Oh, it's already up. Okay, never mind. It's up. So, if we look at this sine wave, right, you can see it doesn't actually start. Like, here's the sine wave, but there's another shape imposed on top of it. So, I want to make my sine wave, which is a constant frequency like this. Like, you can see these individual waves here. But if I can impose this shape on my sine wave note, it starts hard with a ding when you hit it with the mallet, and then it fades out as the vibrations die out, right? And it ends on a 0. So if we can impose this shape on my sine waves, it might sound more like a marimba. Where's the xylophone one? Maybe we can look at the differences. Music. VX, where's the X? Music, xylo, note. So a xylophone, you can see, actually starts in even harder. So if we zoom out, like there's this nice easy ramp up here while the note gets louder and then it dies off. It's using probably a soft mallet. But on the xylophone, they're using a harder mallet, so it's a harder ding in, right? And then it actually takes longer also to, like it dies off faster, and then it slowly fades, unlike the marimba. Different materials, different sound profiles, but the underlying principle is still the same. We have something that, this is like maybe a more metallic sound, I guess. Whereas this one is more of a wood sound. But we have noise on top of what we would consider a sine wave, right? So this is kind of a messy sine wave, isn't it? For the xylophone, unlike the marimba where it's very regular. It's not perfectly shaped sine wave, it still has its own noise on top of it, but it's much more predictable. So that's interesting. So how can I take a sine wave or a triangle wave and impose these kinds of shapes over the life of the note? That's kind of the question. Now, my thought is we can create a profile for magnitude and just multiply the sine wave. Then we can apply a noise factor to it. We could use, like, say, a Perlin noise. There are two things we could do there. So these two both have kind of the same problem. It's hard in and it's hard out. When we want either fade in, we want to control how we come in while the sound comes to life, and we want to control how we go out. So we want to probably impose a magnitude shaping, right? To add noise for warmth. A lot of those warm sounds that you hear are going to be about having more natural shapes in your sine wave, unlike the mechanical shapes we have right now. So those are kind of my first two thoughts for the sounds. So let's talk about imposing a magnitude shape. If I take this sine wave I just generate it, that's fine. But then over the course of the duration of the note, I want it to see, I can think of too many different options, too many complicated things. We should start simple. The sound itself. Hmm. Or just variation. Like a lot of people claim that there's more warmth and character to listening on a vinyl as opposed to a digital recording. That's because the digital recording is always 100% the same every time. Whereas in a vinyl, there's a little bit of wiggle and bounce to that needle. And there's it just adds that little bit of, they call it warmth, but really it's more organic or more analog sound to it. And I don't have a ton of time, so impose magnitude shaping. That's probably the first step. Oh, that's right. Okay, so I know what we did there. Playing with sound. Hmm. I guess that all goes away. We haven't used that in forever. If it's slowed down, interpolate. If it's sped up, play the average of the samples. And zero fill. So basically, zero fill is fine. It needs to go here. Magnitude shaping. So the sample count oh, we apply out elsewhere. Okay, so we can't actually do that. Anywhere where the contents of out plus plus. If it's slowed down, we do it there. If it's sped up, it's there. Zero fill, I don't care. So we have two locations. So if we have a duration, have that volume. And this first one does not have to sound good at all. And it can be hard-coded. We're not worried too much about playing these sine wave issues. Blah, 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 math, audio. we're not playing slowed down, so even for our first pass, we don't have to worry about that one. We can just come to here, compute those. The volume, let's get our t value. Float t equals something, which is our sample count over data point to max samples as a float. That's our t. And let's just ramp it up over the duration of the note. Volume times t. This is the heart of it. Now, how we choose our what t maps into is different, but let's. So it should, the note should build and then halt abruptly, which is not great. Now, we can make it so that it dies off instead of builds up. Easy enough. We just take this 1.0 minus that. Just so you get an idea what kinds of things we can do here. So let's hide that for now, which OBS, there we go, hide audacity, okay. Oh, that's not the worst thing I've ever heard. You can hear that there's no pop at the end because it always is at 0 because we have shaped it. Let's see here, where's the star scratch? We have shaped the overall shape so that it dives. So the first one we did was just a climb. As the thing went on, it got louder. The one we just did, and that's just multiplied by this sine wave. So we still get the same number of waves, but the magnitude is shrunk. The same when the last one we heard that sounded like a ping and then dies off. As if we did, we just multiplied the whole thing by a descending linear, right? So we can come in hard. It's at full volume at the start, like we hit something metallic with a metallic metal, but then it loses its vibrations very quickly. That gives it that kind of ping sound the ding, ding, ding we were hearing. So that's what we were doing. So, I mean, ideally, we could have whatever shape we want defined in an array of values and interpolate into that value. But let's play with it a little bit more before we go down that road. This is kind of fun and fascinating and explorative. This also will absolutely screw things up if this is an infinite running note. What if we parameterize P using an easing curve? Sound HPP. Float P equals ease. So we do a quadrian out. We could do a bounce. That could be fun. We can not do an elastic. So many options. We can do bounce. Let's just try a ease E by way of easing method quad in out. So let's try that. See if that makes it sound a little better. Oh, we're not using P. Times P. Oops. Not that. Let's see. Yeah, here we are. I would argue that sounds better than the last one, which was a linear. Kind of cool what we can do already. I want to try the bounce out. Just because I have no idea what it will do. It'll be like a run. Adds a little vibrato there. Okay, let's try with the bounce in. And when we get really spicy, we can try bounce in out, just to see what we get. Oh, that's actually kind of cute. Interesting. Bounce in out. We're just playing around. We're just having fun here. All right, Travest, time for bed. You have a wonderful evening. Sleep well. See you tomorrow. I will be 5 or 10 pounds heavier tomorrow because of donuts, but well, I will be here. Huh. Okay. So these are kind of the kinds of things we might consider. But I think ultimately what we want to do is interpolate an array of values. There are so many things wrong with the way we're doing this right now. We're not doing it in case we're slowing time. This is easing methods only, and some of these easing methods go outside of 0 to 1. We're not checking anything about the value. We're not checking to see if it's an infinite playing sound. So many issues. But as a means to try things out, this is not bad. Now we're doing all this with triangle. What if we try it with sine? Let's go back to our song. Just hear how sine wave sounds with the easing curves. Amazing how much mileage I get out of these easing curves. So many times you just want to take a number between 0 and 1 and give it a shape. So the sine doesn't sound that much different. Now the problem with these easing curves is that they all basically start, well, We either basically have to start all off or all on, and there's not really a way to make a nice shape. So I think we do need to go with an interpolate and array method. All right, so let's go play with this. This needs to be a setting, or a sound. And we need different methods to do the shaping. We have waveform, easy enough. Enum class, not a waveform, a shape. Shape is none. Quad in, out. What else did I say? The bounce in, out was reasonably entertaining. Interpolation array 1. We're just gonna stub this out. Shape names. So yeah, an instrument is going to be a combination of noise levels, noise type, maybe. And shapes that we're applying over the top of it. For infinite sounds, we can do interesting things, or we just decide that the first quarter second of a sound is shaped and then maintains and then falls off at the end for long sounds. So maybe there's an in and out curve, actually, for shape. Maybe there's two shapes applied to each tone. So many options. Now let's just harden this up a bit. Where are these waveform names? They're there. And we need to know how long the in and the out are. And the in and the out durations have to be longer, have to be shorter than the full duration. We are not going to do any shaping on a sound that goes forever, I think. We're just going to apply a shape for now. We may have a shape in and shape out, and a shape in time and a shape out time. Oh gosh, there's so many things we could do. If I had infinite time, we would do them all. Okay, so Clang has better debugging output, at least. Yes, that's the error messages are much better. Looks nicer. I didn't expect any code to really break or any launch options. Okay. And it definitely compiles faster. Compile time is a big deal, man. You don't want to get caught with oops, what did I do? Don't have infinite time. So one thing there are just too many things to think through here. Too many variations. Then we also have things like noise, which we've not played with, and we might not have time to play with. So let's do this. Shape in, shape out, shape time, float, shape in time, shape out time. So when we set an instrument, it will set a wave, basically instrument. This is the instrument. Main body of the volume should remain at 1. Shape in, shape out, shape in time, shape out time. Let's do a balance. Wait, quad. Oh, interesting. Quad in, quad out, quad in, out. We'll try some different things. It costs us nothing to code these up right now because they're so similar. 2, 3, 4. Bounce in, bounce out, bounce in, out. 4, 5, 6. We're just using these as placeholders for now. Yeah, I keep thinking I should switch to Clang someday. For some of my projects at least. Right, so down here where we initialize everything, signal data object. This is how we pass it to their engine basic, or the data we need. Shape in, sound, shape, none. Zero point 125, 125. Noise. Okay. Now we have to do this here and here. So I'm thinking we need to go through a helper function. Static float magnitude shape given sample count max sample count what do we call it? Shape in, shape out, float in time, float out time. T in, T out, probably. Let's just play with this idea then. Float T equals sample count divided by max sample count. Okay, if T is less than Tn, we should assert a whole bunch of stuff. Assert sound. Does sound have assert? Yeah, okay. Assert Tn is greater than 0. Assert that T out is less than 1. And assert that T in is less than T out. So if our maximum sample count max sample count is less than 0, sound has no duration limit. Otherwise, we can do fun things here. Oops. All right, quick restroom break. Just a moment. Okay. So we're just going to ignore this case for now. Because here could do some default thing with in, assuming some t in. So we could, in other words, have a sound come in a certain way. Okay, so we can flip t, blah, blah, blah. If our t is less than the time in, then what result? Well, the t depends. Okay. So we need to do a switch on whatever our shapes are. Case sound shape none. Oops. Okay, now all we have to do for this is result equals ease t over t in. So in other words, if we say that t in is 1/8 of the duration of our sound, and we are partway into that, what we want to do is ease over the t in. So that makes sense in my head. Easing method, linear. Strictly not necessary. Oh. No, we'll just, okay. Let's just do quad in. Quad out. Quad in, out. Bounce in, bounce out. Bounce in, out. Okay, so that's if t is in the start. If t is greater than t out, then we switch based on out. Maybe we change the name of t real quick here. Percent done. Then we can compute t equals percent done over t in. Now this is just always t. Everything in this part always has to do with t. our percentage done, percent done. Okay, so percent minus T out is how much remains. So if our T out starts at like 0.75, well, it's 0.125. Oh, the way I'm thinking about it is this. So if I say the time in is 0.125, so 1/8 of our sound, and T out is 1/8 at the end, then our percentage has to be greater than 1 minus that. So if we say our T out is 1/8 of a second of the sound, then our percent has to be greater than 0.75. So if our percent, if 1 minus our percent, so if we're at 0.8, if we're at 0.9, right, then it's actually 0.15 in to this region, 1 point something into this region. I think it's like that. Except I think that these two need to be reversed because we want to walk through the T backwards. So instead of walking from 0.875 to 1, I actually want to walk from 1 to 0.875, which I think means I flip these. Is it 1.0 minus all of this mess? So this will give me a positive number all the way down to, so if our percentage is 100%, if our percent complete is 1, then 1 minus 1 is 0, over T out doesn't matter. If it's 0.875, then that's 125 over 125, which is 1. I think this is it. Just this. I think. It does nothing. No return. Okay. So our default sound is none. So up here, P equals the magnitude shaping given sample count max samples data point to shape in data point to shape out data point to shape into good evidence. Shape out time times P times P Is that it? So we can make sure it sounds like the mechanical sine wave again. Is private. Oh. Well, the good news is, I actually have to put it here. Just declare it up above and file. Yeah. Okay. Okay. So in theory, this will sound back like the. Whoa! Oh. Okay. I know what that's about. Time in, time out. Time in plus time out must be less than 1. Okay. We'll do a full clean. I don't remember what all I've changed. Maybe it's necessary. Yes, tonal shaping. I don't know. Do you think if we go down this road, we'll have to manually turn our own interpolation stuff? But it's kind of cool. Could be kind of cool. I think probably the best thing is to just have an interpolation array. That we can use. I'm probably not gonna have time to add noise today. Okay, so we're back to sounding terrible. But now, quad in, quad out. So every note should be a little bit smoother in and smoother out. Yeah, so both the in and the out were better. What do you do? Quad in, out? On both sides, but that sounds even more smooth. Smooth. We add linear. We can add linear. Whoa, 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 come back. So here's what linear would sound like. We can make this a little bit longer too. Not handled in switch. That's probably true. Okay. Well, we have some options now. Okay, let's add one called inter. You know what? These switches feel shockingly identical and can be factored out. Like this. And then sound, shape equals in. equals sound shape none. Shape equals shape in. Shape equals shape out. And then it runs the switch statement no matter what. That feels clear. Okay. So interp right now does nothing. What we need for interp to work is we need an array of data. Float interp array static const int interp count. I don't know, doesn't matter. Now, looking back at let me think. Well, we can start at 0. One, two. Let's actually, what I'm going to do, I'm going to make a spreadsheet. LibreOffice Calc. Which you probably, do I need to show? Let's make 16 points. 0.0. Oh, okay. 0.0, 0.0625, and then I can make that 16 values, right? 0, 1, 2, 3, 4, 5, 6. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 17. We get 17 points. I'm just going to plot this real quick. Let's see here. Insert chart. Line. Finish. Okay. I just need to make this look like a thing. Insert another chart for this other region, make it a line chart as well. I know that I want to, well, I mean, we might as well show this screen. Oh, my eyes are irritated again. Plus window capture, LibreOffice. That is not LibreOffice. Holy smokes. What is that? Okay. That's not what I said. I said LibreOffice. You stupid manure. Good heavens. All right. Remove. How it got Chrome out of LibreOffice, I don't know. Or I just need to have. Okay. Irritated eyes, the worst. Okay. Add. Window. No. Nope. Nope. Window capture. LibreOffice Calc. It is? Oh. Okay. So here's what we're looking at. I can resize things a little bit. If I want an in curve, smaller Maybe that's too small. 0, 5. About here we want to be at the 0.5, so 0.1, 2, 0.25, 3.25. Feels a little aggressive. Well, we jumped 7 here. Nine, 6, 8, 9, 9, 4. One, 0. And basically, this is just a quad in out, right? Go 0, 0. 5. I want to go up pretty quickly, I think. Hmm. 0, 2, 5. I want this thing to peak, or to peak later than the halfway mark. Or not, I want it to be more aggressive. Here we go. Let's 2, 7, 5, 2, 7, 5, 2, 7, 5. Two, 8, 5. I can drag these points, but I don't think that's how that works. Ramp up slower. 0, 2, 5. 0.75. 1.
Yeah, yours is a little small, but
That one. This one, 0.65. Okay. We're just trying to shape a curve that looks, oops, reasonable. Slow build up. For 7. For 6. Just push some of these down a bit. 4, 5, 3, 4. 3, 5. 6. 3. Okay, I think this one wants to be a little bit smaller. A little bit smaller for 3. Okay, so this curve looking up here is pretty good. We need to climb pretty fast, but not that fast. 65. 64. Not that one. 6. Something like that. Let's do it with 0, 0. Oops.
oh man. Oh, look, it's you, cutie pie.
Okay, so if we take these values, and put them in here. Roughly like that. Terp array 1. Terp array 2. What we want is for this one to fall off a lot gentler, so. $9.75 or 1. 0.975. Sheesh. 975. Oh no, that's not what I mean. I want it to fall off even faster and right out to 0. Okay, so point 0.05, 0.1, 0.15, 2. All right, so you kind of see where we're going here. Most of the way. Maybe even this is too steep. Maybe like 0.9. $65. Okay. Oops. 0, 4, 3, 7. Oh, 9. 12, 5. 15, 16. 19, 5. Maybe all the way to 20. Hmm. 25. 28. 29. Okay. I want this one to actually fall off the cliff even faster. 0.41. Oops, 30. Two, 5. Oh, 27, then 29. That should be 25. 2. Mm-hmm. 20. 18, 5. 0.0. Okay. All right, still these numbers. These will be interp 2. Okay, we have 2 interpolation arrays now. Interp 1, interp 2. Okay, so I've got these 2 interpolation arrays now, and I'm gonna have to quit soon. So basically, we take our t divided by our interp count. Interp array 1, interp array 2. These are auto reversed, aren't they? So I actually think I have to swap these. You know what we can do though. Sort lines. Boom, reversed. Check that action. Okay, so what we do is that we take t times in, let's see, something, interp count. Tells us where in the array we have to go. Index equals, now, int index 1 equals int of index. Int index 2 equals index 1 plus 1. Okay, then the t remainder equals index minus I1 then all we need to know is remap. Do I have that anywhere in like keys or in math? Right, well, t tells us how far between the 2 points we go. So we take the value at index 1, take the value at index 2 equals interp array 1 at index 1 Volley 2 equals interpolate 2 at index 2 equals, what we take is basically solving a line, which I don't have time to finish this out and test it. Shoot. Because it's basically value 1 at index 0, value 2 at index 1. Then we just draw on there until we hit t on the x-axis, or the remainder here. So it's y equals mx plus b. Now b is at 0, we cross the 0, so let's just draw a line here. By the definition of what we're trying to do, this is at x0 and x1. And we have value 1 and value 2. So the b is 0, slope is rise over run. So v2 minus v1, rise over run, which is 1, times the remainder. So let's say that our remainder was 0.5, and we're halfway in between the two. Oh, and then we add v1 back in. Okay, so what percentage of the slope did we cover? This is this part, and then plus the offset to v1. Okay, that's not too bad. V equals v2 minus v1 times remainder plus v1. If it's negative, it's fine because this negative, and then we're adding the thing back in, it should be fine. V result equals V. Okay. Now, if we go to initialization, we can try this. Interp 1, interp 2. And we're going to take like 6, 5. And like 1, 2, 5. We're just going to see what happens. Shape equals shape in. Excuse me. Oh. Shape is set but not used. It should be used right here. All right, let's see how it sounds, and then I have to call it. I gotta go to my donut date. Got things to do. I've got donuts to eat. No, there's some bad popping, which means we've done something terrible. What if we give it same shape in and out. Interp 1, interp 1. Oh, let's see. That did not make a difference. For 1, we didn't actually change which array we were interpolating. 2 and 2. For 2, the T should reverse things. So that's fine. It's kind of working because I can hear it come into the sound. I wonder how much just go quad in out. Quad in out. Quad in out. And we just make that short and that long. 0.75. Shorten that up even more. Not much time to come in. Well, anyways, we get the idea, sort of. Let's try triangle song. Put triangle back in. I don't know if it'll make much of a difference with so much shaping. You might not hear the difference much. And then I gotta go eat donuts. So we're just about up to 80s bad synth, which is better than we were. Like I said, the interpolate probably needs a little bit of debugging, but not much. Yeah, we're probably gonna call it there. Since we're in journal, let's finish it out here. Make the tones sound better. Sound. And now do some shaping per note. Hard coded. It sounds better, but needs more work. Like I said, we've got a couple of options. We've got different things we can play with. We still need to add noise. Note shaping. I'm not sure I like the in and out portion. Maybe just shape the whole note. So we'll take it up to that note. Noise. I don't like the in-out shaping. Maybe just a whole note shaping interpolation over the whole thing, not just the in-out. So we still got some things we can try. Once we have that and the noise, we should be able to make different tonal instruments. Things that come in hard and leave soft and vice versa. And then we'll apply those instruments as we go. So let's save this. Git status. Some tone shaping is working. Hard coded. Needs more work. Yeah, we're gonna call it there. So thanks for joining. Tomorrow's Compiler's Day if I can get out of bed because of donuts. So you have a wonderful evening. Happy Halloween. And we will see you tomorrow for compilers. All right. Bye-bye.